Dear learners, in the first part of basics of petroleum, we have learned about the usefulness of petroleum in our life, the origin of petroleum and the petroleum system elements, and I talked about the source rock characterization part. In this portion, we are going to talk about the other parts of source rock characterization. Okay, in this slide, we are going to talk about the organic carbon richness. Now, if you remember, in the last part, I told you about three elements of source rock characterization: the organic carbon richness, the kerosene type and the thermal maturity. So, let us begin with the organic carbon richness. What is organic carbon richness? We also call it the total organic carbon percentage. Organic carbon is calculated from rock eval pyrolysis. You remember the S3 peak that I talked about, which measures the carbon dioxide. So, from there we have one portion of the organic carbon, but even after heating the sample till 550 degrees Celsius, there might be some carbon dioxide left in the sample. What we do is we take that sample and we put it in an oxidation oven kept at 600 degrees Celsius to oxidize the organic matter or the kerosene, which gives us any residual organic carbon that is still there within the sample. Now, if we add these two up, what we have got from rock eval pyrolysis and from the oxidation oven, we get the total organic carbon. What do we do with that data? Just by looking at the total organic carbon, you can classify how good the rock is. So, if you have a organic carbon content 0 to 0.5 weight percent, you would say the source rock is poor in quality. On the other hand, if you have more than 5 weight percent of organic carbon in that source rock, you would describe it as a very excellent source rock. So, just by looking at the organic carbon, you can form an idea how good the source rock is, how rich the source rock is, which in turn tells you how much oil or gas can be generated from the source rock if you expose that source rock to right kind of temperature environment. Now, let us learn about the kerosene type. All three things, organic carbon richness, kerosene type and thermal maturity, are interlinked, and together they give an idea about the source rock characterization. Now, you see this graph, the vertical axis is atomic hydrogen over carbon and the horizontal axis is atomic oxygen by carbon. Where do we get this data? Again from rock eval pyrolysis. We get the number of the hydrogen and we also get the total organic carbon, and we can also have the oxygen and total organic carbon from our S1, S2 and S3 peaks. If you plot the data, we typically see the kerogens can be divided into 4 groups: type 1, type 2, 3 and 4. Type 1 and type 2 are the best type of kerogen, which gets formed either from marine algae, which is type 1. If it forms from marine phytoplanktons, then we call it type 2. Now, type 1 and type 2 kerogen has lot of hydrogen than oxygen. So, they generate volumes of hydrocarbon. Type 3 on the other hand has lot of oxygen compared to hydrogen, and type 3 kerogen is formed from land plants. So, if you have a large swamp area and the land plants get deposited there and they get buried, we get kerogen type of 3. Kerogen type 3, since it has less hydrogen and more oxygen, it is prone to generate more gas rather than oil. So, depending upon which type of kerogen you have, if you expose it to the same temperature, it will generate either oil or gas based on what type of kerogen is there in the source rock. Kerogen type 4 is basically not useful for our purpose. This is the kerogen that forms when it gets the organic matter gets exposed to oxygen or the organic matter is oxidized. So, kerogen 4 type 4 has no potential to generate oil or gas even if you expose it to the right kind of temperature. So, we learned about organic richness, that is how much organic matter is there which can generate hydrocarbon. We also learned about kerogen type. So, you can understand that it is not only the organic richness, also what kind of kerogen is there, that also determines how much volume of oil or gas we can get from that source rock. Now, the third important part in this story is the thermal maturity. What is thermal maturity? There are two factors by which we can measure thermal maturity of the source rock. One I have already talked about in the first part, which is the T max. There is another indicator which is called the vitrinite reflectance, which is presented as RO. Now, what are vitrinites? Vitrinites are nothing but a constituent of macerals. Maceral is nothing but, as you have minerals in the rock, in the organic matter you have macerals that are there. As you increase temperature and the source rock gets more and more mature, the reflectance of the vitrinite changes, as you can see in this picture of thin section. So, RO number, smaller number means that the source rock is less mature. As the RO number increases, the source rock is more and more mature. Using these two indicators, that is the vitrinite reflectance and the T max data coming from the rock eval pyrolysis, you can immediately understand what is the thermal maturity of the source rock. And also you can see the thermal maturity depends on the kerogen type also. So, now with all these three data, you can easily characterize a source rock, that is how rich it is, how much oil volume it could have generated, and what is the temperature that is exposed to. All this gives you an idea how much volume of oil or gas could have been generated from this source rock. Let us go to the next petroleum system element, which is the reservoir rock. Now, we have the source rock which has generated hydrocarbon. We need a place to store this hydrocarbon also. Where does this hydrocarbon get stored? It gets stored in reservoir rock. What is a good reservoir rock? A good reservoir rock should have porosity and permeability. Now, what is porosity? Porosity is the empty space within the rock between the grains that can store hydrocarbon. And what is permeability? Permeability is connectivity of those pores through which the fluid or the oil and gas can flow within the rock. Let us look at an example. This is a picture of a rock. Now, as you can see, the grains are connected to each other. There is no empty space within the grains. So, this is an example of a non-porous and non-permeable source rock. What do you see in this picture? You see grains and you see pore spaces between those grains, but those pore spaces are not connected. So, this is an example of a porous rock, but a non-permeable rock. Now, this picture you have porosity and the porosities are nicely connected. So, fluid can move through the rock. So, this is our ideal reservoir rock, which is a porous as well as permeable. Now, you understand what is the characteristics of a good reservoir rock. Now, if I give you this picture, you can easily understand this is a thin section of the sandstone. On the left hand side, you see a lot of blue spaces, those are nothing but the pore space. So, you can immediately tell me which one is a good reservoir rock out of these two sandstones. Of course, the left one, which is having porosity and permeability, is a better reservoir rock. Now, most common reservoirs are sedimentary rocks, and among those The typical reservoirs that we see all over the world are sandstone, limestone and also some shale. Now, we also see reservoirs or oil found within volcanic or igneous rocks, which are naturally fractured. So, volcanic and igneous rock, as you know, does not have any inherent porosity or permeability. But since these rocks are very brittle, in different conditions they get fractured, and those fractures act as artificial or secondary porosity which can store hydrocarbon, but this is not common. About 40% of the world's oil is actually found in limestone type of reservoirs, and about 55 to 60% of the oil in the world is found within sandstone type of reservoirs, and about 5% of igneous rock are also there where we find hydrocarbons. The two pictures that you see are thin sections from a very good sandstone reservoir, and on the right hand side you see a thin section of very good carbonate or limestone reservoir. As you can see, there are ample porosity with both in these rocks, and these porosities are also connected. So, both of these constitute very good reservoir rock types. The third petroleum system element that I talked about is the hydrocarbon traps. Now, what are hydrocarbon traps? Now, you have a source rock which has generated hydrocarbon. The oil or gas from that source rock has now come into the reservoir rock, but you need to close that reservoir, right? Otherwise, the hydrocarbon will escape and ultimately exposed and get lost. So, to store that hydrocarbon within that reservoir rock, you need a cap. Traps are nothing but those caps which are basically a non-porous and non-permeable rock which lies adjacent or on top of the reservoir rock to store the hydrocarbon within the reservoir rock, so that it does not escape. Now, there could be different type of traps, basically 4 type of hydrocarbon traps: the structural trap, the stratigraphic trap, hybrid trap and hydrodynamic trap. So, what is a structural trap? Structural trap are nothing but a trap formed due to structural elements within the rock. It can be an anticline where the seal, the cap rock, non-porous rock, caps the reservoir rock and the oil and gas cannot escape. Or it could be in a faulted situation where the good reservoir rock is capped by, on the other side of the fault, by a seal rock or cap rock, and again oil and gas cannot escape. So, any trap related to the structural element is called a structural trap. What is a stratigraphic trap? Here the trap is formed due to stratigraphic variation. On the left hand side, as you can see on the top picture, there is a reservoir rock which got capped by a roof rock or a cap rock because of unconformity. In the picture below, you see the oil and gas get capped by the same strata, but because it got changed its characteristics and lost its porosity or permeability due to diagenesis. So, in that same strata, at one portion forms a reservoir rock, at a different portion it forms the cap rock and stops the oil and gas to migrate out of that reservoir rock. This is an example of salt dome related stratigraphic trap. Salt, as you know, is completely impermeable. So, any reservoir rock that gets juxtaposed against a salt dome forms a trap. Stratigraphic traps can also be formed within isolated geological features, like isolated channels within a shaly section, or even a riffle structure within carbonate mud can also form a stratigraphic trap. Now, after understanding structural trap and stratigraphic trap, you can easily understand what is a hybrid trap. Hybrid trap is nothing but a combination where both stratigraphic element and structural element play a role to form a trap. As you can see in this picture, this is a half graben tilted fault block structure which is capped by a non-porous impermeable rock, thus the hydrocarbon gets trapped. So, it has a structural element as well as a stratigraphic element involved. The fourth kind of trap is called the hydrodynamic traps. It is not very common, but there are places where you do see hydrodynamic traps. What happens here? If you have an undulating structure, syncline, anticline feature, and if you have large groundwater flow through that reservoir rock, the flow of the water traps the oil or gas in the kinks of the fold. The typical thing here is the contact between the oil and gas and the water will be tilted here. This kind of trap is known as hydrodynamic traps. As I told you, this is not common, but there are places where we do see existence of hydrodynamic traps. All right, so we have talked about the three elements of the petroleum system. The fourth very important element in this is the hydrocarbon migration. What is hydrocarbon migration? Now, migration can be of two types, primary migration or the secondary migration. What is a primary migration? Now, you have this source rock which at high temperature generates hydrocarbon, that is oil and gas, and thus the pressure within that rock increases, which causes creation of micro fissures. The hydrocarbon that is generated within that source rock goes out of that source rock through those fissures, the pressure goes down and the fissures close. This kind of migration, where the hydrocarbon is expelled from the source rock, is called the primary migration. What is the secondary migration? Now, as this oil and gas goes out of the source rock, it needs to travel to a reservoir rock, right, which we call carrier bed, until it gets stopped by a cap formation. This migration through the carrier bed or the reservoir rock itself is called the secondary migration. Now, please understand that migration is a very slow process and it can be extended to large distances, right. So, migration from the source rock to the reservoir rock can happen tens of kilometers or over hundreds of kilometers of distance, and the rate at which migration happens vary between 0.1 meter per year to even 100 meter per year. So, imagine a source rock and a reservoir rock combination which is there about 100 kilometers apart and large volume of oil or gas is generated, how slow that process will be to transfer that oil or gas that is generated in the kitchen to the reservoir rock. So, it is a very slow process. Also, interesting fact here is that only 40% of the hydrocarbon that is generated are actually gets trapped. What happens to the others? They either never comes out of the source rock or they get never trapped and get exposed and leaked out on the surface of the earth. Let us summarize what we learned so far. So, in this lecture we have learned about the source rock and how we measure the quality of that source rock and the maturation of the source rock. We also talked about reservoir rock types, and finally, we talked about different types of hydrocarbon traps and hydrocarbon migration. Thank you.